We have one shape left that we're going to discuss, and that is having 6 electron domains. The shape for that one will be octahedral, and that again is based on 6 locations that our electrons are found. So 6 bonding is our first example with 0 non-bonding, and the shape will simply be octahedral. If we knock off one of these bonded and replace it with a non-bonded, the shape that we're going to have will be square pyramidal, square pyramidal. And again, we'll look at the shapes here in just a moment. The last one that we actually will talk about here is having 4 bonded and 2 non-bonded. And for that one, we're still looking at square, but it'll be planar. Square planar will be the shape. Okay, let's bounce over to our site. FET is the site again. We're going to get rid of these non-bonded pairs to begin with, and we'll add in a total of 6. 4, 5, 6. So there's our shape. And again, the shape we're looking at here is something called octahedral. So we have 6 locations. I think the reason we call it that is because it has 8 faces. If you think of this as being like a solid, and you can draw like a plane between each of these 4 on top and 4 faces on the bottom. So there'd be 4 faces on each one of these. You have to kind of fool around this and see if you can figure that out. But there would be 6 faces that you would have on this structure. Okay, so this is again octahedral both on the electron and the molecular domain. If we knock off one of the bonded pairs and add in a non-bonding pair, there it is, we get what we call square pyramidal. And again, the bonded, non-bonded pair here on the bottom, pretend that's not visible. We're just looking at the molecule itself. So at the base, you have a square, and it makes up a pyramid if everyone connects to that top point up there. So octahedral electron domain, but what you see, the molecule, is square. Knock off one more, and we'll add in another lone pair. And the shape that you see, again, is a square in a plane. So it's like a piece of paper, square. Here's the center, the purple, and then the 4 corners are the other molecules, or the other atoms, excuse me, onto that plane. That's the last one. Okay, so we won't need this anymore. We'll just bounce back over to our notes. And we'll look at a couple more names. Now, what you may want to do is, have these guys here in front of you. I'm going to pull out, well, actually, we'll get some names here first, and then we'll talk about this more in a second. First thing we'll do is we'll mention the idea of another model hybrid orbitals. So the idea of that is that the s and p orbitals, so if you remember going back to our periodic table, that the s and the p blocks, these are the electrons, the valence shell electrons that are involved in all of the bonding. The d's, for the most part, we'll talk a little bit more in a few minutes, aren't involved in the bonding of the electrons because these are on the outside. Remember, if I'm in the 4s and the 4p's, 3d's are a whole level down, energy level. 4th energy level, 3rd energy level, 4th energy level. These guys are on the outside, and those are the ones doing the bonding. There's 8 of them. So we have these 8 electrons on the outside. Okay. Now, the s and the p, even though they're on the same energy level, the p's are at a higher energy level than the s's. And that makes things a little complicated as far as when you're making a shape that's tetrahedral. They all look the same. So how could you say the s's and the p's are different energy levels if they all look the same? So we say they blend together in a hybrid. So the s and p orbitals blend together to form equal energy orbitals. And based on that, I'll talk here and I'll give you an easy way of understanding it. If you have one S and one P, it's always going to be an S, but if you have the S and one of the P's that blend together, in other words, they form similar locations for electrons to be found. If those bind together, the shape of the molecule will be linear. In other words, you have two locations that electrons are found. They have hybridized to fix that molecule. And if it does, you're going to have a linear shape. If I have two of the p orbitals that blend together with the s to form three identical locations, so the s and two of the p's hybridize together to give you a shape, that shape will be trigonal planar. And if we have all three of the p's orbitals, the sublevel, blend in with the s, that'll be sp3. And again, that shape will be trigonal. And I put that down too well. Tetrahedral. That'll be our shape. Let me bounce this up because that wasn't visible. Trigonal. What? Trigonal tetrahedral. No, I'm looking at my notes wrong. That'll be tetrahedral. So if you have the S and the three P's combining together, that'll be tetrahedral. Let's bounce over to that FET site just so I can use that as a bit of an example. So we'll get rid of these guys here, 1, 2, and it looks like it'll work. So again, based on the ones that are hybridizing together, and this may or may not work here, we'll just take a look and see if I can work this in. If, I guess I'll use this as an example. If I have this location, I have two locations where the electrons are found, an S and one of the P's blended together to make these guys look the same. And that works out. So this would be sp2, sp hybridization. And really the easy way of doing this, if you go back and take a look at your sheet of paper, I have two locations, and think with the superscripts, the numbers on top, if they're both ones, adds up to 2, right? 1, 2. This is linear. If I add in a third, and I have 3, so this one would be the S, I'm just making that up, and this is a P and this is a P, they blend together so they all look the same. They have hybridized to look the same. I have a total of 3 electron domains, sp2. The superscripts add up to 3. I have 3 electron domains. It works. As far as the shape goes, take a look, it's trigonal planar. And the third example is if I have all 3 of the P's and the S blend together, that's going to make this shape here that you see, which is tetrahedral. So that'll give us this shape that we see there. They all blend together so they have the same energies. Okay, bounce back to our notes. So I think this sheet's probably about done, and we'll move on to another. Let's look at how multiple bonds fits into this whole conversation. We mentioned that, I think, a little while ago, in the first lecture, actually. Multiple bonds. That is the combination of the first time we've talked about this, what's called a sigma. I'll write that down. Sigma bond and one or more pi bonds. And this was in another lecture that I had just as far as going over the PowerPoints. And I'll see if I can pull something together here in the next video. But right now, I'll just kind of put this together and then we can talk more in a couple minutes. So again, the combination of a sigma bond and one or more pi bonds. As far as the energies go, the pi bonds are less energetic than the sigma bonds. So sigma bonds are stronger. And typically what you think about as far as a bond, a single bond particularly, but anytime you have a bond, you always have a sigma bond. The pi bond is the extra, the second bond, if you will. In a double bond, the second bond is the pi bond. If it's a triple bond, you always have this, always, every single time. And then the other bonds are both pi bonds. So one is a sigma, the other two are pi. Let's assume you have sp3. For each multiple bond, there is an unhybridized sp pair above and below the plane. Okay, I can see I'm running out of time, so we'll come back in and we'll talk a little more about this in the next lecture.